The death of a warship usually arrives from below in the form of a physics equation that solves for total destruction. A modern heavyweight torpedo, like the American Mark 48 ADCAP or the Russian Type 65, does not impact the side of a hull like a battering ram. It is far more intelligent and far more cruel. It swims 40 feet beneath the keel of a target, sensing the specific magnetic anomaly of the steel above. When it detonates, 300 kilograms of PBXN-103 high-grade explosives turn into a superheated gas bubble in a fraction of a millisecond. This creates a massive vacuum that lifts the center of the ship out of the water, snapping its spine like a dry twig. Gravity then takes over as the bubble collapses and the vessel breaks in two. This is the backbreaker effect or the bubble jet phenomenon, and it sends destroyers, frigates, and cruisers to the bottom in minutes. But there is one class of ship that looks at this physics of destruction and defies it. In 2005, the U.S. Navy towed the decommissioned aircraft carrier USS America, CV-66, to a classified location in the Atlantic Ocean. For 4 weeks, they bombarded it with torpedoes, cruise missiles, and planted internal demolition charges. They wanted to see what it would take to sink a supercarrier. The ship refused to die. After 25 days of punishment that would have obliterated a small fleet, the Navy had to board the vessel and open the scuttling valves to finally send her down. The survival of a Nimitz or Ford-class carrier is not an accident. It is a masterclass in redundancy, armor, and human will. While popular media focuses on the thickness of the steel or the shape of the hull, the real secret is hidden much deeper. It lies in a classified architectural feature known as the Side Protection System, SPS. A multi-layered sandwich of steel, fuel, and void space designed to absorb the energy of a nuclear blast. It lies in the electronic screaming of the Nixie decoys that drive torpedoes insane. And it lies in the hands of 5,000 sailors who are trained from day one to fight water and fire in pitch darkness. In this documentary, we are going to dissect the anatomy of the unsinkable. We will open up the hull to reveal the void-liquid-void defense layers that act as a crumple zone for the ocean. We will analyze the shock trials, where the Navy detonates 40,000 pounds of explosives next to a manned ship to test its nuclear reactors. We will explain the Knuckle Maneuver, a desperate turn used to blind enemy sonar with a wall of turbulent water. And we will answer the ultimate question. In an age of hypersonic missiles and supercavitation torpedoes, is the aircraft carrier still the king of the sea or just a massive floating target? To understand why an aircraft carrier does not break in half, you must first understand the sheer scale of the structure and the materials involved. An Arleigh Burke-class destroyer displaces roughly 9,000 tons. A Nimitz-class carrier displaces 100,000 tons. This is the square cube law in action. The keel of a carrier is not a single beam running down the bottom. It is a massive, box-like girder system constructed from HY80 and HY100 steel. HY stands for high yield. This steel was originally developed for submarine hulls to withstand the crushing pressure of the deep ocean. On a carrier, it is used to withstand the violent upward heave of a torpedo detonation. This steel has a yield strength of 80,000 to 100,000 pounds per square inch. It is designed to bend before it breaks. When a gas bubble lifts the ship, the hull flexes. It groans. Radar dishes might snap off the mast due to the whipping effect. But the structural integrity holds. The ship absorbs the energy that would snap a smaller vessel, distributing the shockwave through a complex lattice of heavy frames and longitudinal stringers that run the entire 1,000-foot length of the ship. The flight deck itself acts as the upper flange of this box girder, providing immense stiffness to the entire vessel. But the primary defense against torpedoes is not the keel. It is the Side Protection System, SPS. This is the single most important, yet least understood feature of carrier survivability. If you look at the blueprints of World War II battleships, you see thick belts of face-hardened armor plating designed to stop shells. On a modern carrier, armor is only one part of the equation. The hull is designed as a multi-layered absorption system. It typically consists of 5 distinct vertical bulkheads extending inward from the outer skin. The first layer is the outer hull, relatively thin steel designed to trigger the contact fuses of incoming weapons or to fragment upon impact. Behind that lies a void, an empty compartment filled with air. The blast wave enters this void and expands, losing kinetic energy because there is no medium to transmit the shock effectively. The next layer is liquid. These tanks are filled with either marine diesel fuel (DFM) or seawater ballast. Liquids are incompressible. When the shockwave hits the liquid layer, the energy is hydraulically distributed across a massive surface area of the inner bulkhead, rather than concentrating on a single point. It turns the piercing strike of a spear into the blunt shove of a wall. This process is known as hydraulic loading, and it dissipates the lethal energy of the warhead over hundreds of square feet of steel. Behind the liquid is another void, a dry space that acts as a final buffer to catch any leakage or shrapnel. Finally, there is the holding bulkhead, a wall of high-tensile armored steel that protects the citadel, the vital spaces containing the weapon magazines and the nuclear reactors. This SPS is essentially a massive shock absorber. A torpedo might tear open the outer hull and flood the side tanks, causing the ship to list, but the vitals remain dry. The ship effectively sacrifices its outer skin to save its heart. However, the best armor is the armor you never have to use. The carrier fights an invisible war underwater long before a torpedo strikes. This is the domain of soft-kill countermeasures. Hanging off the fantail of every U.S. carrier are the AN/SLQ-25 Nixie decoys. These are towed acoustic generators, streamed on fiber optic cables thousands of feet behind the ship. A modern torpedo hunts by listening for the specific acoustic signature of the carrier's 4 massive bronze screws. The Nixie acts as a digital ventriloquist. It captures the sonar pulses of the incoming torpedo, amplifies them, and sends them back with a time delay or a frequency shift. This confuses the torpedo's guidance brain, making it believe the carrier is actually a mile behind its true position or moving in a different direction. The torpedo attacks the decoy, detonating harmlessly in the ship's wake, blowing up a piece of equipment worth $50,000 to save a ship worth $13 billion. The Nixie system has evolved over decades, now capable of countering sophisticated wake-homing torpedoes by generating complex acoustic jamming patterns that mask the ship's physical wake. If the electronic seduction fails, the carrier attempts a kinetic defense. This is the realm of the anti-torpedo torpedo (ATT). This is a relatively new and classified layer of defense, often part of the Surface Ship Torpedo Defense (SSTD) program. The carrier fires a small, high-speed interceptor designed to collide with the incoming threat. It is a bullet hitting a bullet underwater. The ATT uses its own active sonar to track the incoming torpedo and maneuvers to impact it directly or detonate a fragmentation warhead in its path, destroying the guidance section or triggering the warhead prematurely. And if all technology fails, the helmsman executes the knuckle. The carrier accelerates to flank speed, over 30 knots, and executes a hard-over rudder turn. The 4 massive propellers biting into the water at maximum torque create a chaotic zone of turbulence and cavitation bubbles. To a sonar sensor, this cloud of bubbles looks like a solid wall of noise. The carrier turns behind this knuckle, hiding its acoustic signature in the chaos of its own wake, breaking the lock of the weapon. This is a maneuver born of desperation, but one that exploits the physics of sound in water to create a temporary shield of noise. But let us assume the worst case. The torpedo finds its mark, the SPS is breached, Water is roaring into the engineering spaces at tons per second. This is where the human element becomes the primary defense. On a commercial ship, the crew abandons ship. On a U.S. Navy carrier, the crew fights the ship. From the first day of boot camp at Great Lakes, every sailor is trained as a firefighter and a damage controlman. This culture of damage control is what truly makes the ship unsinkable. The vessel is divided into thousands of watertight compartments. When the general quarters alarm sounds, a distinctive rhythmic gonging noise, the ship sets material condition zebra. This means every watertight door, hatch, and scuttle is bolted shut. The ship becomes a honeycomb of 2,000 isolated steel cells. If a torpedo floods auxiliary machinery room 1, the water stays there. It cannot traverse the bulkheads to flood the rest of the ship. The danger of flooding is not just sinking, it is capsizing. If the ship takes a massive hit on the starboard side, the weight of the water will cause it to list. If the list exceeds a certain degree, flight operations are impossible. Jets will slide off the deck and the intakes for the emergency diesel generators might be submerged. The Damage Control Assistant DCA in the Central Control Station, known as DC Central, has a solution: counterflooding. With the flip of a switch, powerful pumps begin sucking seawater into the tanks on the undamaged side of the ship. Or fuel is transferred from starboard to port. This intentional flooding adds weight to the high side, pulling the ship back to level. During the Battle of Midway, American damage control teams saved the USS Yorktown by counterflooding, allowing her to launch aircraft even after taking heavy bomb damage. That doctrine remains the Bible of the modern fleet. The pumping capacity of a Nimitz-class carrier is staggering. The fire main system alone, powered by massive pumps, can move tens of thousands of gallons of water per minute. Specialized eductors, pumps that use water pressure to create a vacuum, can suck floodwater out of the bilges faster than most hull breaches can let it in. The sailors fighting the damage operate in hellish conditions. When a torpedo hits, the power often dies. The regular lights go out, replaced by dim red emergency battle lanterns that cast long shadows. The air fills with smoke, steam, and the smell of burning electrical insulation. The water entering the ship is not clean. It is a freezing sludge of oil, hydraulic fluid, and sewage. Sailors form shoring teams, using wood beams, Douglas fir, and telescopic metal jacks to reinforce weakened bulkheads against the immense pressure of the water pressing against them. They use soft patches made of rubber and Jubilee clamps to seal ruptured high-pressure pipes. They do this while the ship is rocking, while the hull is groaning under the stress, and while secondary explosions may be rocking the deck. They rely on sound-powered phones, archaic but reliable devices that use the acoustic energy of the voice to transmit orders without electricity, ensuring communication lines remain open even if the entire grid fails. The philosophy is drilled into them: don't give up the ship. The most critical asset to protect is the nuclear reactor. Critics often ask, what happens if a torpedo hits the reactor compartment? The engineers at naval reactors have anticipated this. The reactor vessel, the steam generators, and the primary coolant loops are not welded rigidly to the hull. They are mounted on massive, shock-absorbing rafts. When a blast hits the hull, the steel skin vibrates with a high-frequency whipping effect that can shatter rigid pipes. The shock rafts isolate the nuclear components from this violence, allowing them to float inside the compartment. Furthermore, the reactor has an automatic scram function. Sensors detect the shockwave of an explosion milliseconds before the hull deforms. The control rods are pneumatically fired into the core, stopping the nuclear reaction instantly. Even if the ship sinks, the reactor compartment is designed to remain sealed, creating a sarcophagus that prevents radioactive contamination of the ocean. This design was validated during the shock trials of the USS Theodore Roosevelt and the USS Gerald R. Ford, where charges were detonated nearby to ensure the reactors could survive near misses without leaking. Finally, we must address the ocean itself. The competitor's script mentioned 60-foot waves as a threat. For a destroyer, a 60-foot rogue wave is a survival situation. For a Nimitz-class carrier, it is merely a bad day at the office. The stability of a carrier comes from its metacentric height (gm). The center of gravity is low, the engines, the millions of gallons of fuel, and the weapon magazines are deep in the hull. The center of buoyancy is high. This creates a massive righting arm. The further the ship rolls, the stronger the physical forces push it back to vertical. The flight deck is 60 feet above the waterline. While waves may crash over the bow and damage the catwalks or wash away antennas, the risk of capsizing from sea state alone is statistically zero. The only real danger is to the aircraft on deck. If a 30-ton fighter jet is not properly chained down with heavy-duty tie-down chains, it becomes a wrecking ball. But the ship itself, it rides the storm. The hull is designed to flex in heavy seas, a phenomenon sailors call the shimmy, where you can actually see the long passageways twist slightly as the ship hogs and sags over massive swells. This flexibility prevents the steel from cracking under the strain. In 2005, the sinking of the USS America proved the point. The Navy did not just fire one torpedo, they attacked it from the air, from the surface, and from below. They placed demolition charges in critical corridors to simulate internal sabotage. The ship soaked up punishment for 4 weeks. It settled lower in the water, but it remained upright. It remained buoyant. It took a deliberate, calculated effort by demolition teams opening the sea valves to finally send it to the bottom. This test proved that sinking a U.S. carrier requires not just a lucky shot, but a sustained, overwhelming saturation attack that few nations are capable of delivering. The data from that test was used to refine the design of the Gerald R. Ford class, making the newer ships even more resilient. The Ford features improved armor alloys, a reorganized internal layout to minimize fire spread, and an electrical grid that can reroute power around damaged sections instantly. The aircraft carrier is often called a floating city, but that is a soft metaphor. It is a floating bunker. It is a honeycomb of armored steel designed to absorb kinetic energy, heat, and radiation. It is a machine that is kept alive by the sweat and courage of 5,000 sailors who know exactly which valve to turn when the water starts rising. It is a testament to the philosophy that survivability is not just about thick walls, but about redundant systems and trained personnel. If this anatomical dissection of the Navy's Leviathans changed your perspective on naval warfare, I need you to do 3 things right now. First, subscribe to the Tactical Chow channel. We don't rely on myths, we analyze the blueprints. Second, smash that like button. It helps us break through the algorithm's armor. Third, leave a comment below. I want to know, do you believe the age of the aircraft carrier is over due to hypersonic missiles? Or does this level of survivability make them relevant for another 50 years? Let the debate begin. And finally, if you think surviving a torpedo is intense, wait until you see the brutality of tank warfare. Click the video on your screen right now to see what happens inside an M1 Abrams when a depleted uranium sabot hits the armor. It is physics on the edge of madness. Click it, and I'll see you there.